In this presentation, I'll cover audio recording by defining it and outlining its process. Real generically speaking, audio recording is the process by which sound information is captured onto a storage medium, like magnetic tape, optical disc, or solid-state drive. Now, of course, nowadays it's just solid-state drives, but for many years it was magnetic tape. And then for many years after that, it was optical discs like CDs or mechanical hard drives. Okay, that's the definition, and here is the process real simply. First, you need to convert sound waves into electricity. That's always step one, is to turn sound into electricity. And that's done with a transducer. Microphone is the most obvious, but there's also tone wheels and pickups. Tone wheels are in Hammond organs, and pickups are underneath strings of guitars and basses. And then you need to store that information somehow. And many years ago, it was a tape recorder, but nowadays it's just solid-state hard drive. And then, of course, you need to play it back. And the playback machines and loudspeaker systems are also going through a period of flux. So like everything else in modernity, this is the simple process that still remains true, but the details are in the process of changing. Let's look at the details for each of the steps. First step, you need to convert sound waves into electricity. That's done via a transducer. And the most obvious versions of a transducer are a microphone and a loudspeaker. They are opposite ends of the spectrum. A microphone converts your sound into electricity, and a loudspeaker converts the electricity back into sound. And then the storage mediums, as I briefly alluded to, it's all solid state these days. But for thousands of years, it seemed like it was optical discs and CDs. And then for thousands of years before that, it seemed like it was tape decks. But unless the apocalypse descends upon us, it will be solid state moving forward. Now, the playback machines and loudspeaker systems today often take the form of a smartphone and a set of headphones. Okay, so how people listen is not always under your control. And if you can get people to listen to your music on their car stereos, then that's the best option we have, really. But most people are listening on headphones or Bluetooth speakers, or who knows. So mixing is a bit of a compromise art form. You need to mix for all of these playback and loudspeaker system eventualities. So once audio has been converted from analog to digital, it only ever returns to analog when made aloud by loudspeakers. So for the most part, everything that we do with processing and mixing our audio these days just takes place in the digital realm, and the sound is only ever analog at the very beginning and at the very end. This is also maybe 20, 25 years or so new. Just for years, it was analog all the way, right? You had analog microphones going to analog consoles, going to analog tape machines, going to analog effects processors, all analog. But nowadays, of course, we are squarely in the digital realm. So everything in between, editing, mixing, mastering, and so on, takes place digitally on either side of the transducer spectrum. This is all probably pretty obvious, but this is the first piece of hard stuff. So we should know exactly what's happening with digital audio. What is digital audio? Digital audio is produced via pulse code modulation, PCM, which entails sampling audio and turning it into a digital code that can be interpreted by a computer. And here's how it works. A computer listens to an audio signal at discrete moments, many thousands of times per second. And it converts each one of those time samples into a numeric code. And that's what PCM is, pulse code modulation. The computer listens at specific moments, and it creates a numeric code for each one of those moments. And the speed at which your computer performs this conversion describes its sample rate. So you may have heard that in the terms of digital audio, maybe looking at a CD and it's got a sample rate. Maybe you've dialed in your DAW and had to configure a sample rate. That's the number of times per second your DAW is listening. Now, the most common sample rates for digital audio is 44.1 kilohertz, which means that it's creating 44,100 samples every second. So that's mind-numbingly high, but
Wait.
higher sample rates exist. Go ahead.
Can you say that number again?
Yeah, 44,100 samples every second. That's what 44.1 kilohertz means. So K is abbreviation for 1,000. So 44.1 is actually 44,100. Higher sample rates exist. There's 48, 88.2, and even 96. Okay, let's take a closer look at what this sample rate business is up to. So the Nyquist theory stipulates that the lowest possible sample rate that can be used to reconstruct analog audio is twice the maximum frequency. And since humans hear up to 20,000 hertz, also known as 20 kilohertz, the minimum sample rate for digital audio is 40,000. Okay, let me try to make sense of this by using smaller numbers and this picture here of a waveform. Okay, so here's a model of a sound wave. It has peaks and troughs corresponding to compression of air molecules followed by rarefaction of air molecules. Let's consider a sound at 1 hertz, which performs 1 cycle per second, or has 1 peak per second, or 1 trough per second. If we're moving left to right across this little graph paper chart I drew, that's time. Each one of those peaks, 1 a second. Like here's second 1, here's second 2, here's second 3. That waveform would have a frequency of 1 hertz. Nice and simple. And then say we had a sample rate also of once a second. Here computer was like, okay, I'm going to make a sample once a second. That means it would be tuning in here. I'm going to make a sample, and then it'll tune in again here, make another sample, tune in again here, make another sample. And that's great, but it's missing the other half of the waveform. It's missing what happens at a half a second later instead of a full second later. So in order to get analog audio converted to digital audio of 1 hertz, you would need a sample rate of 2 hertz. That's the Nyquist theory. It not only has to be able to listen here, it also has to be able to listen here halfway through the wave's life. So that means it would have to listen twice for every time the sound wave performs one of its dances. That's why the sample rate has to be twice as high as humans can hear. So humans hear up to 20,000. The minimum digital audio sample rate is 40,000. But the common digital audio sample rate goes a little bit better. It actually goes up to 44,000. So it's built-in redundancy. So my example was this is a sound wave of 1 hertz happening 1 time every second. In order to capture enough information to recreate the sound wave, you would have to be listening at 2 times per second, at twice as fast as the sound, so that you may get both up and down. At bottom, the sample rate is capturing specific amplitude levels in time, which means every time the computer opens its ears and listens, it's going to make a little numeric code that represents at what point along the waveform it was. And the easiest way to understand is with a 4-bit code, which has 4-digit sentences like 0111 or 0011 or 0001. So using a digital code of 1s and 0s, the 4-bit code allows these little 4-number sentences. And if you take all of the possible permutations of 1 and 0 using 4 available slots, you get these 16 numbers. Now imagine if we took those 16 numbers and we plotted them on the amplitude axis of a sound wave. Amplitude, of course, is the height of the wave, and that corresponds to volume. That means with 4-bit code, you have 16 available locations at which to plot our amplitude. And here along the graph paper, we see that we have plotted 4-digit sentences representing one of these 16 available amplitude slots. That's 4-bit audio. Now, similarly, if you had 8-bit codes, then you would have 8-digit sentences like 11010011, twice as long.
Okay.
And that would give you 256 possible amplitude values. Imagine if I had the wherewithal to draw on graph paper. Instead of 1 through 16, I drew 1 through 256, and then these were 8-digit long sentences. And then you would have way more options at which to plot your amplitude, thereby giving you more fidelity. You can think of this in terms of a pixelated picture. A 4-bit code is going to be very pixelated, very boxy. Right? You zoom into a digital image that has very low resolution. You start to see weird shapes and pixels that don't correspond to reality. It's the same thing with digital audio. And obviously, 4-bit code is going to give you very weird Atari-like sounds. That's what digital audio sounded like in the 1980s. Now imagine if we had 16-bit code. A 16-bit code, which means each one of those digital sentences is 16 numbers long. That would give you 65,536 possible amplitude values, which is pretty accurate, especially compared to 4 or even 8-bit. So a sample rate of 44.1 kilohertz and a bit depth of 16 means that 44,100 times per second, the computer is creating one of those 16-bit sentences and plotting it along one of 65,536 possible amplitude values. And the recreation of the sound wave then occurs by a connect the dot style pointillism. So here's the analog audio, which is a smooth curve, but digital audio is a connect the dots type pointillism. Now, of course, if you're dealing with 65,536 possible dots, you can imagine that you're essentially perfectly recreating the analog audio. You would have to be a computer to hear the difference. That's what audio resolution is all about, sample rate and bit depth. Obviously, higher sample rates and bit depths gives you a higher fidelity character of audio. When you're producing digital audio, it's important to be clear about your system's bit depth and sample rate. Indeed, whenever you set up a new song or a new project in your DAW, that's the first thing it asks you about. It's like, hey, what's your sample rate and bit depth? It's okay to work at CD quality, 44.1 and 16 bits. It's a little bit easier on your computer system as far as RAM goes and processing power. But you can work at much higher levels, but eventually you do mix down to CD quality to upload to the internet, because I think that's the maximum resolution and sample rate provided by streaming services like Spotify. I could be wrong about that, or it could be changing in the future. Problems may occur if you change the sample rate and bit depth of your audio project mid-project. Say you're working at one sample rate and bit depth, and then you bounce it down to another. In order to do that, your system has to employ a process called dithering, which maintains the integrity of your sound by adding noise artifacts. The problem is this results in slight temporal distortions to your audio file, and you may notice these time deformities if you try syncing this audio with some other related project. The disparate sample rates and bit depths might give you some temporal distortions. Very slight, but noticeable over time. The best practice here is to decide on one sample rate and bit depth and stick with it through the duration of your project. When you are prepared to export your final mix, you should do so at 44.1 and 16 bits. This is the industry standard for music distribution, including compact discs and streaming services. If you are to take the art and craft of audio recording seriously, you must own both an analog to digital converter and a DAW. DAW is a computer-based audio production system like Pro Tools, Cubase, or Studio One, and an analog to digital converter is a device that converts your analog audio into digital audio. And this Focusrite is a common one. Other common analog to digital converters include PreSonus, AudioBox. Okay, so next we'll explore the basic process of recording, mixing, and finalizing music. To successfully record musical audio, you need to set up a guide track. A guide track usually comes by way of a click track, drum loop, or scratch track. A click track is a metronome. So here I am setting up the metronome in my DAW. So you just select what sound you want to happen and how fast it should go. And then you can play your music there, and it's a guide track. It keeps you temporally square. But you can also do this with a drum loop. So you record some fragment of drum set play, and you configure it so it repeats predictably over time and makes a good solid beat. You can set that up as a guide track. If you're without a click track and you're a drummer, you might be able to set up your own guide tracks. Indeed, this is how they did it for years. All that great 60s recordings, Motown, these were usually rhythm sections, drummers and bass players, guitar players, who could keep a good beat. And they would set up these fantastic guide tracks or rhythm tracks in the form of what's called today a scratch track. That means you just get the band to play the song one time through as best as they can. A good way to capture a good scratch track is have the drummer listening to the metronome, and then the rest of the band can play along with the metronome. And if the rest of the band can handle it, then they should be listening to the metronome as well. But back in the day, they were a little bit more free. They would just rely on a good, solid drummer. And anyways, making scratch tracks is fun. Set down something good and useful that you can further produce into a good song for commercial consumption. The scratch track, consisting of drums and bass and some harmony instrument like piano, say, that's often called a rhythm track. Okay, so I might set down a guide track with a drum loop. So once you have that guide track or scratch track, the next step is to add some harmony. Now, you might already have some harmony in your rhythm track. If you have a guitar or piano, you might have harmony. So, of course, harmony is more than one note played simultaneously, also known as chords, and usually configure some sort of chord sequence. And this is what constitutes harmony. Right? So I just played A minor, then I played the D9, and then G7. Right? Maybe go to C, major 7. That's your harmony. So if you lay down a guide track of drums, you might begin adding harmony. Now, sometimes the harmony and the bass and the drums are recorded simultaneously, and if they are, that's your scratch track or your rhythm track. But you can also construct them one at a time, and you should probably begin with drums or a metronome. Okay, once that's configured, you got your harmony and melody and drums. You should set about adding some sort of lead melody. Now, the lead melody is usually provided by vocals or lead instrument like trumpet, saxophone, synthesizer, guitar, etc. You might also add some supporting melodies, which is a subservient melody to the primary, usually background singers or some sort of harmony singing. And once again, this is typically provided by keyboards or strings or guitars, background vocals. Lots of fun to be had there. So you got the rhythm track, got some harmony, lay down a primary melody, maybe add some supporting melodies. And then the icing on the cake is to add nuance and flair via sound effects and drum fills, hand claps, auxiliary percussion, and many other varieties of ornamentation. Once you have everything, that concludes basic tracking. You have all the sounds that you know you're going to use. After that, the next step is to edit or revise all of your captured material so that it proceeds in a mistake-free and smooth fashion. So this means you remove mistakes, nudge the performances into alignment with the click track, tune all the lead instruments, make some composites, which is what I was up to in this project here. As you can see, I was really trying to compile many takes into continuity performances. And I was just hammering away at this project for days on end. I didn't really get there yet, but I will eventually. But what's left basically is to do the editing, find the right sounds, and then make sure that they are configured to unfurl in a way that is perfect and mistake-free. That is the domain of editing, and obviously making sure that you remove unwanted sounds like mouth sounds and amplifier hiss. Okay, once everything is edited into alignment, then you can begin doing signal processing, which consists of running your captured audio through electronic components meant to adjust volume level, dynamic character, and frequency response. So this includes reverbs, delays, equalizers, expanders, gates, all that good stuff. If done well, signal processing will result in a more refined and brilliant character of audio. Signal processors are largely responsible for the hyper-real and three-dimensional style of audio common to modern pop. Though I am not a huge fan of all modern pop, I do admit it sounds better than ever. The engineers and the editing and the signal processing and the digital audio really does sound amazing. And much of that is born in signal processing. Okay, once that's all accomplished, the last step is to finalize your file. And this is generally referred to as export or bounce or mixdown. What you are creating is a stereo file meant for commercial consumption. What I do in my DAW is set the export range to the length of the track. I set a loop indicator around the length of the track, and then I click Export Mixdown. And once I've exported a stereo file from my DAW, I have an audio file that's ready for uploading, sharing, or use in another media project. Any further processing that's made to your finalized audio file constitutes mastering, which entails dynamic processors and equalizers applied to the stereo file itself. Okay, the goal of this presentation was to introduce the concept of audio recording and lay out the basic process for recording music, but I barely scratched the surface of either topic. There's much more to learn. To gain a mature understanding of audio recording and music production, you'll have to spend many years recording and producing audio. I've been pursuing this skill for a good long time now, but I've still got a lot to learn. There's many ways that my audio recordings can improve, and I'm working on that. But it's a process. It's a lifelong process. It's a bit like being a musician. You just have to keep going at it. It's the journey, not the destination. Just keep learning and you'll get better. Thanks for listening and watching, and I'll see you next time.